Okay, let's go ahead and get started now. So, okay, we're gonna get started now. And we're gonna finish up on fluid and electrolytes and start respiratory. That's my goal anyway. And anybody have any questions on anything at this point? Okay, then I'm gonna go ahead and okay. So I'm going to go ahead and open up this is where we were ready to start from the other day on acid-base balances. The last thing we talked about was calcium levels and hyperkalemia and hypokalemia. So that leads us right into another aspect of fluid and electrolytes, the acid-base balance. Exciting topic for a Wednesday morning. However, this is another one of those areas that is real critical to your patient. They care, they may not be aware of what it is, but they pay very close attention to their acid-base balance because your patient can get into a world of hurt in here. We generate carbon dioxide all the time from our mitochondria. That combines with plasma to form carbonic acid. That always drives our blood pH down. Now, our blood pH is normally right around 7.4. And we have a very narrow window of normal. 7.35 to 7.45 is normal. A little too much CO2 and we start dropping down. We become more acidic. Now, fortunately, our medulla oblongata recognizes that drop in pH and says, let's breathe faster to get rid of the CO2. That's how we regulate that. But it's always a battle between pH wanting to drop and CO2 being produced, because we're always producing CO2, always. And the more glucose we burn, the more exercise we do, the more CO2 we're going to generate. You know, I've been saying since the beginning of AP1, it isn't oxygen needs that drive our breathing rate. It's to blow off the CO2 because we got more oxygen than we need in our blood. But we're always producing CO2. CO2 levels will rise when you climb a flight of stairs and you breathe faster because you're breathing faster to blow off the CO2 that you've made. Has nothing to do with oxygen. So remember, every pass through your body every time a red cell makes a circuit in your body, your blood only gives up 20% of the oxygen that's in there. Okay, problems with acid-base balances. As I've been saying here, metabolic activity is going to create acids. You get lactic acid from your muscles. If you don't have available oxygen, if you're in oxygen debt, your muscles are going to make lactic acid. You are going to break down nucleic acids. The DNAs are going to release phosphoric acid. If you break down fat, you're going to have fatty acids and ketones. You're going to have that fruity odor. And of course, the big one is CO2 from, carbonic acid from CO2. So our pH range is very sensitive to us. As I've said, our arterial blood is set at about 7.4. We're slightly alkaline so that we can be compensating for the carbon dioxide that we're releasing. If we get above 7.45, we are in what we call alkalosis. We are getting too basic. And if we get below 7.35, we're in acidosis. And our enzymes are very, very sensitive to changes in pH. Our enzymes, enzymes are globular proteins. They're sensitive to temperature, they're sensitive to pH. If they get too acidic, or that's okay, too basic, they become denatured. Amylase, which works in our mouth to break down carbohydrates, does just fine at 7.4. But you put it in the stomach at 2 because of the hydrochloric acid, and it doesn't function well at all. In fact, it breaks down. So we have to we have to try and maintain our pH levels, so our enzymes don't start shutting down. So, and we see the scale, you remember, I'm sure you remember this from AP1. It's on your head to make you feel better. But there's the pH scale. Distilled water is pH of 7. It's neutral. And we can see that urine and saliva are 6, and coffee is 5, and acid rain and tomato juice. You don't hear much about acid rain anymore. Vinegar, gastric acid, pH of 2, hydrochloric acid in the stomach, pH of 1 to 2, battery acid. There's still acid inside our batteries, by the way, car batteries. It's usually sulfuric acid. It's like pH of 1 to 0, very, very acidic. The scale is a logarithmic scale. And what that means is as we go from pH of 7 to pH of 6, something that is pH of 6 is 10 times more acidic than 7. And a pH of 5 is 10 times more acidic than 6 and 100 times more acidic than 7. As we go down the scale, we have a 10-fold increase from 6 to 5 to 4 to 3 to 2 to 1. So it's all driven by the presence of hydrogen ions. Hydrogen ions, just is what we call a proton, the hydrogen with a little plus beside it. The more hydrogen ions we have, the more acidic we are. So now acids, anything that's an acid, it gives up hydrogen ions. The more hydrogen ions you release in solution, the stronger the acid is. Hydrochloric acid dissociates into the hydrogen and the chlorine, and you give up lots and lots of hydrogen, so it's a very strong acid, as opposed to carbonic acid, which is a weak acid. The bases are something that accept hydrogen ions. So strong bases grab hydrogen ions quickly. Weak bases sort of receive them slowly. Something like sodium bicarbonate, baking soda, is a weak base, and it sucks up hydrogen ions, but not rapidly. Sodium hydroxide, like oven cleaner, the original oven cleaner type stuff you spray on inside the oven if you clean your oven. It's mostly sodium hydroxide, a very strong base. It will burn it will dissolve away your skin. I still remember when I was in general chemistry and they were demonstrating some of these acids and bases, and they gave us these pellets of sodium hydroxide to hold. And what would happen if after it set in your skin for a few seconds, the skin was starting getting slippery, it was dissolving the skin cells and releasing the fat from underneath. Didn't hurt, but they were trying to demonstrate to us why you don't touch some of these things, so probably wouldn't be allowed to do that anymore. So, but I'll never forget that. So, okay, now let's move on here. Okay. Now our bodies are constantly regulating our acid-base balances. We have a series of buffers to do this. We don't like being acidic. We don't like being basic. The chemical buffering system is the most important buffering system that we use. That's something, circle that, put a star on it. The chemical buffering system, carbonic acid and sodium bicarbonate. We get responses in seconds. We're always trying to neutralize an acid or a base. And so we use carbonic acid and sodium bicarbonate. It is the most important of the chemical buffers. It acts quickly. If we get too acidic, we neutralize the acidity with sodium bicarbonate, but we also have a second response. If we get too basic, we neutralize usually with carbonic acid. That's acts within seconds. So if for whatever reason we are slightly alkaline, we're going to neutralize that with carbonic acid. If we're slightly basic, I'm sorry, if we're slightly acidic, we're going to neutralize that with sodium bicarbonate, baking soda, essentially. Now, that is seconds. The second way we regulate acid base is with our lungs. We have a physiological response with our lungs. We breathe faster or breathe slower. Now that takes a long time to kick in, about 3 minutes. And as far as our cells go, that could be considered a really long time. But 3 minutes, because when you run up a flight of stairs, by the time you get to the top of the stairs, or maybe a little bit right after that, you're going to notice that you're breathing faster. You're not going to be breathing faster as you start running, because you've got plenty of oxygen and you haven't generated a lot of CO2 there, because you've got all the oxygen you need. Your CO2 levels are normal, and you start running up the stairs because you don't want to be late for class. You want to be there on time, or early, and something like that. I didn't say. I said nothing. So, yeah. But you don't start breathing fast until you get to the top of the stairs, until you're already up the stairs, because it takes about 3 minutes for the system to spin up and for your medulla to detect, hey, well, first of all, you got to generate the CO2. You're going to run you're going to be running off of creatine phosphate and anaerobic for the first 30 or 40 seconds, and then you're going to get into electron transport and Krebs cycle, and all that stuff's going to kick in, and that's going to take about 3 minutes to get to that point, because to start burning glucose in the level to get the energy you need. So after about 3 minutes of exercise, you're going to be giving off CO2. And your medulla is going to detect that, because it's not going to monitor CO2. Your medulla is going to monitor blood pH. It's the simplest way to track CO2. And so they said, medulla, hey, pH is low. We better breathe fast to blow off the CO2. It doesn't know that it might not be CO2. It could be fatty acids for all it knows. But it's going to say, hey, you got pH is low, let's breathe faster, for good or for bad. So that's the downside of having just a simple approach here. However, in most cases, it's going to work just fine, because most of us aren't going to be going into a ketoacidosis event. Remember ketoacidosis? Person's having a diabetic emergency, the cells are starving, so they start breaking down fat to convert it to glucose. And when you break down fat, you end up releasing the fatty acids and forming ketones. Your patient in ketoacidosis smells fruity, breathes rapidly because of all the acids in their system. Medulla doesn't know that it's not carbon dioxide. So one of the characteristic signs of a diabetic emergency with ketoacidosis is rapid breathing and a fruity odor. Remember you all know the smell of fingernail polish remover. It's not an unpleasant odor. It's caused by acetone. Acetone is what we call a ketone. We're busy making ketones in our bodies as we break down the lipids to convert to glucose. So we smell fruity. It's the best way I can compare. But we're also releasing all these acids. Medulla doesn't know what it's caused by. Just all it knows is that you got acids, so I'm going to breathe faster. But the best part about that is it's a good clinical sign something's wrong. Anyway, respiratory regulation takes 3 minutes. We always breathe fast after exercise. If we're burning up glucose, we're going to breathe faster in about 3 minutes. And then the last one is the kidneys. The kidneys will kick in. The kidneys will start secreting hydrogen ions or retaining hydrogen ions. The only thing wrong with the kidneys is that they're slow. It takes several days to spin up to do that, to have any noticeable effect. So the fastest system is the chemical buffering with carbonic acid and sodium bicarbonate. We don't even notice that. The one we always notice is we're breathing faster after exercise. The our lungs breathe faster to blow off the excess CO2, and we don't notice what our kidneys are doing. But if it becomes a chronic issue, our kidneys are going to get to work. But again, that takes several days. So now within the buffering system, there are 3 types of buffers. The most important one is the bicarbonate system, using sodium bicarbonate and carbonic acid. We also have a phosphate buffering system and a protein buffering system, but the most important one is the bicarbonate system. It uses sodium bicarbonate, baking soda essentially. If our body is acidic, we try to neutralize that with sodium bicarbonate, sucking up the extra hydrogen ions, and we end up with a carbonic acid. So if if we have a strong acid, we try to bring it down to a weak acid. So if we are acidic, we try to neutralize it with sodium bicarbonate and end up with a very mild acid. That's the whole basis of the chemical buffering system with bicarbonate, carbonic acid. If we're too basic, we use carbonic acid. So this is the most important system here in buffering: sodium bicarbonate, carbonic acid. If we're acidic, we use the base sodium bicarbonate. If we are basic, we use the acid carbonic acid. The idea is if we use if we're dealing with a strong acid, we can neutralize it to a weak acid. If we're dealing with a strong base, we can neutralize it to a weak base. So, but this is the #1 buffering system in our body. This will start working in seconds. You know, and we aren't aware of it because, you know, we're not monitoring, we're not consciously monitoring anything. So the medulla is doing all the work. So if we're acidic, we neutralize it with sodium bicarbonate. If we're basic, we neutralize it with carbonic acid. That's what you need to remember. The most important of the buffering systems, the fastest is the chemical buffering. And of the 3 chemical buffers, this is the one that matters. We use this more than anything else. And if we overwhelm that, then we go to the respiratory and we start breathing faster. Okay, phosphate uses, it's very similar to carbonic acid and bicarbonate, only here we're using phosphate and phosphoric acid. So just for your information. And proteins, it uses certain amino acids. Again, it's just the 3rd mechanism. Okay, 2 conditions that cause problems for us. Acidosis and alkalosis are very, very serious conditions. They really alter how we act. If we are accumulating hydrogen ions, we're going to become more and more acidic. If our pH is dropping, meaning that we're getting more acidic, our respiratory rate's going to go up. The CO2 level is going to go up, it's going to go down. Our bicarbonate level is going to go down to try and bring our pH back up. So if you follow the red arrows there on the left-hand side, if we are in an acidotic state, sounds so technical when I say that. If we are in an acidotic state, first thing that's going to happen is that we are going to, within 3 minutes, start breathing faster to get rid of our CO2 levels. So our CO2 levels will drop. Our carbonic acid levels will drop. We want to, so we're going to blow off the CO2, and we're going to be neutralizing the acid that's forming, and our pH should start coming back up. We don't notice it. So if you exercise, if you do anything and you discover that you're breathing faster, then at that point, you know that your respiratory system has kicked in to get rid of the excess CO2. If you're breathing faster, when you're doing something, you're puffing a little bit, that's because you're now trying to get rid of the CO2. Your respiratory buffering respiratory mechanisms have kicked in. So you can say, hey, oh, my medulla oblongata is telling me to breathe faster now because I've gotten slightly more acidic. That's exactly what's happening. So now, on the alkalosis side, if we get too alkaline, excuse me. I knew it was coming. I was just hoping it wouldn't. So, okay, if we get too alkaline, the medulla slows down our breathing rate. Instead of breathing fast, we breathe slow because then we retain CO2. So now we can make the carbonic acid we need to neutralize the alkalinity. For example, if you have a patient that's hyperventilated and blown off all their CO2, so CO2 helps to maintain our blood pH. If you blow off all the CO2, the pH is going to go up. We depend on carbonic acid to keep us right around 7.4. You blow off all that CO2, you're going to become alkaline. One of the biggest problems you have with someone who is hyperventilating is that they're getting more and more alkaline. They're moving from 7.4 upward. And so what you got to do is get them to slow down their breathing rate. This is the old breathe into a paper bag. Don't put a plastic bag over their head and tie it off. That's not a good approach. No matter how much you want to. Yeah. Somebody, accidentally tied a plastic bag around their head. So no matter how much, no. But the old remedy, breathe into a paper bag. The only reason you're doing that is because you want to try and retain the CO2 that they're breathing out. The more CO2 that they breathe out and breathe back in, the more they're going to be driving their blood pH back down to where it belongs. Normally what happens if you become alkaline, the lungs will kick in, and in 3 minutes, your breathing rate's going to slow down. Slow down to retain more CO2, to raise your blood CO2 levels, raise the carbonic acid levels, and bring your pH back down to 7.4. So all we want to do is get us to 7.4. That's where we belong. We don't want to be above, we don't want to be below. We will fluctuate as we do things, but we will adjust for it. Okay, now, bad things happen. If we get our pH below 7, we can start shutting down the nervous system and your patient will die. If we get above 7.8, becoming more alkaline, your patient's muscles will go into tetany. So the enzymes aren't going to be functioning to keep things in check there, and they'll go into tetany, and then they'll go into respiratory failure, and they'll die. So it happens fairly quickly too. We pay very close attention to this. We don't, a person in cardiac arrest their blood's getting more and more acidic all the time because they're not breathing, or if they are, so because the cells are still alive. So you have to neutralize that increased acidity, among other things. So because it takes, even with brain cells, it takes 5 minutes to die. Muscle cells are going to last for hours. Cardiac muscle cells will last about an hour. Even if the heart has stopped, the cells are still going to be using the oxygen that's available to them. They're going to be still functioning and burning glucose and releasing CO2, but you're not blowing off the CO2, you're getting more and more acidic. So we are very sensitive to these sudden changes like this. Okay. And I've been saying this all along. A lot of text here. Basically, this is a physiological, the respiratory approach is a physiological buffering, meaning the medulla monitors pH. If pH drops suddenly, because of, the assumption is it's a lot of CO2, so we breathe faster to blow off the CO2. That's all we do. This is the physiological approach to buffering. It only takes about 3 minutes to kick in. Like I said, you don't start breathing rapidly as soon as you start doing something a little more strenuous. It isn't until you've done it for about 2 or 3 minutes does the brain kick in, because it takes a little while to bring that up, to get that running. If you are too alkaline, your breathing rate will slow down to retain CO2. Again, it takes about 3 minutes, which is not very long. You don't want to have your patient that starts breathing rapidly as soon as they get up out of a chair to walk. They shouldn't be breathing rapidly walking. They shouldn't be breathing rapidly on a stress test for a couple of minutes if they're healthy. So we've got fairly quick responses here thanks to the medulla monitoring pH. The only time we get, like I said, the only time we get a little fuzzy on this is if we're in ketoacidosis. Now, what happens if we have a problem with the respiratory system? We have hypoventilation problems. We have hyperventilation problems. If your patient can't breathe effectively, is there something wrong where they can't breathe? Hypoventilation drives them into respiratory acidosis. This is a new term, respiratory acidosis. The lungs aren't working properly to get rid of all the CO2. So CO2 accumulates in the plasma. It's driving the pH down. Hypoventilation. Either the breathing rate is depressed, as a person who has taken an overdose of pharmaceuticals or has suffered some sort of trauma to the medulla, their breathing rate may be suppressed. Normal breathing rate 15 times a minute. What if we get down to 4 or 5 or even 10 times a minute? The slower rate, you're not going to be getting rid of as much CO2 as you should. And so we're going to become more and more acidic because we're not getting rid of it. That's why we call it respiratory acidosis. Your patients with pneumonia often develop respiratory acidosis because in pneumonia, you get you accumulate mucus on the alveoli inside the lungs. And it makes it harder for oxygen to get in and CO2 to get out. So you're retaining more CO2. It's essentially, a type of hypoventilation since you're not getting good gas exchange. So, but anything that causes it impairs lung function to breathe at the normal rate of 15 times a minute, anything that's going to slow that down will cause hypoventilation and drive your CO2 levels up. You're not blowing off enough CO2. Now, the other side of this is hyperventilation. You're breathing too fast. You're breathing 20 or 30 times a minute. You're panting, for example. That hyperventilation blows off the CO2 too fast, and you develop respiratory alkalosis. So you can either be in respiratory acidosis or respiratory alkalosis. In respiratory acidosis, you're breathing too slow, you retain the CO2. In respiratory alkalosis, you're breathing too slow and you blow off the CO2. Hypoventilation versus hyperventilation. It's all about, what are you doing to your CO2? Are you retaining it or are you blowing it off? We don't like either one. So And if we can't get things straightened out with our lungs, then our kidneys will finally get around to helping us. And they do a great job. It just takes some time. You know, our chemical buffering systems start fixing a problem in seconds. The respiratory system starts working on the problem in minutes. The kidneys take a couple days. The kidneys will retain or excrete hydrogen ions to control our acid base levels. You know, if we become acidotic because of increased levels of CO2, if we are retaining lots of CO2 and we are becoming more and more acidic, we are sliding into acidosis, the kidneys will respond by releasing more hydrogen ions. After a couple of days, they'll start secreting more hydrogen ions. They're probably at the distal tubule and retaining the the bicarbonate portion of carbonic acid. If we are too alkaline, the kidneys will recover hydrogen ions. So they're going to do the same thing. They're going to get rid of hydrogen ions, or they're going to keep hydrogen ions, but it takes time. Now, if we develop metabolic acids like lactic acid is formed when we are running on glycolysis. You know, you've decided you've run a marathon. You've run 26.2 miles in the marathon. You've exhausted all your stored oxygen in your myoglobin. You are in what's known as oxygen debt. It's not a big deal. Happens all the time with strenuous exercise. You're in oxygen debt, so you are running now off of the stored glycogen. Okay, we do that all the time. You know, we are using the stored glycogen in our muscles. We have more glycogen than we can ever use. We've temporarily depleted the stored oxygen found in the myoglobin. Myoglobin is that pigment in there that makes our muscles red. Okay. It's what we think is blood when we get a steak or a piece of meat that we want it rare, and it has that red liquid there. The blood's already long gone out of the meat. You know, the blood's drained out a long time ago. It would get nasty if it wasn't. That's the myoglobin coming out when you have a piece of beef. We've depleted all the oxygen out of the myoglobin. So we are running off of simply glycolysis. Now, without oxygen, we can't get into the Krebs cycle. So the pyruvic acid that we make at the end of glycolysis, I'm sure everybody remembers, the end products of glycolysis, among other things, are 2 molecules of pyruvic acid. They have nowhere to go in the Krebs cycle because there's no oxygen there for electron transport. So those pyruvic acids are fermented back to lactic acid. Lactic acid is what makes our muscles hurt after strenuous exercise. Go hike up Mount Lafont and back down. Go take one of the steeper trails, and you'll be hurting the next day. You just will. Your muscles will be sore because you burned through the oxygen and you're running on glycolysis. That's because of lactic acid accumulation, and it makes your muscles hurt. But lactic acid is a physiological or a metabolic acid. The only way we can get rid of that acid is through the kidneys. Any kind of lactic acid, phosphoric acid, anything like that, our kidneys have to get rid of. It isn't like carbonic acid or from it found in the plasma. The metabolic acids, the kidneys can get rid of. Your patient that is going through ketoacidosis and breaking down the fats into fatty acids, the kidneys will have to get rid of that for them. So anyway, this is where our kidneys come into play, but this takes time. the first two mechanisms are in play in seconds to minutes. The chemical buffering, carbonic acid, bicarbonate, that's in play in seconds. The respiratory compensation in place in minutes. We breathe faster, we breathe slower. This takes days. So your patient may not have days. So anyway, so acidosis and alkalosis problems. Acidosis, some of the classic symptoms: shortness of breath, increased heart rate, maybe seizures, nausea, vomiting, diarrhea, loss of consciousness, all sorts of bad things that are happening. Alkalosis, confusion, lightheadedness, tremors, twitching, spasms, nausea, and vomiting. Neither one of these are good conditions. So, how do you know what condition is going on? Well, it's hard to tell without getting their blood pH. Now, you can make a pretty good assessment. If their breathing rate is really fast, they're probably sliding into alkalosis. As their breathing rate is really slow, they're probably experiencing acidosis. If they smell fruity, it's definitely acidosis. So there aren't a lot of overt signs here that you can tell. A little blood work though will give you the results. Okay, now problems. Here are the key problems: respiratory acidosis and respiratory alkalosis. The respiratory system isn't functioning properly. So you have a failure of the respiratory system to maintain pH. This is respiratory acidosis or respiratory alkalosis. It's all driven by carbon dioxide. Carbon dioxide is key here. If you retain CO2, your pH is going to go down. If you blow off CO2, it's going to go up. So what you have to do is you have to look at the CO2 level in the blood. That's PCO2. What is the carbon dioxide level in the blood? And there's a very specific range for that. Respiratory acidosis, alkalosis. Now, the beauty of this is that if you have blood work done and they come back as either acidotic or alkaline, they're too acidic or too alkaline, but their CO2 is normal, that immediately tells you it has nothing to do with the lungs. Respiratory acidosis and alkalosis are driven by CO2 levels. If the CO2 levels are normal, then it is not a lung issue. It's a metabolic, it's a kidney issue. It's a metabolic issue. That's the other type of acidosis and alkalosis. Metabolic acidosis and alkalosis. Anything that is not driven by CO2. Look for your bicarbonate level. Your bicarbonate level will tell you here. If the CO2 is normal, look at the bicarbonate level. Metabolic acidosis. Classic example of metabolic acidosis is ketoacidosis. The diabetic emergency ketoacidosis. So, and this is easy to get confused. I'll just don't feel like you're not going to remember it. It's easy to get confused in this. So, respiratory problems, respiratory acidosis. If we can't get gas exchange, if we're not blowing off the CO2 as quickly as we should, we retain CO2. The more CO2 we keep, the more acidic we're going to get. Patients with emphysema may have respiratory acidosis. Their alveoli emphysema destroys their alveoli. It destroys the elasticity of the alveoli. You don't get good gas exchange. Your patient with pneumonia may develop respiratory acidosis. Anywhere where they're not breathing quickly enough, 15 times a minute, or where the membrane is damaged. The medulla is damaged, the membrane is damaged. There's an extra layer of mucus. Something is interfering with the exchange of the gases. So with respiratory acidosis, you retain more CO2. In respiratory alkalosis, you get rid of the CO2 faster than you're making it. So these are the two respiratory issues here. Too slow, too fast. Acidosis, alkalosis. Metabolic acidosis is different. There you're dealing with metabolic acids like lactic acid, like ketoacidosis, like breaking down fats, or alcoholism will cause metabolic acidosis. Person who ingests large quantities of alcohol. Here's one, drugs that are acidic, like aspirin. Aspirin is, the proper term for aspirin is acetylsalicylic, that's a mouthful, acetylsalicylic acid, okay? Most people don't take aspirin to kill themselves, but many people take aspirin accidentally in an overdose. Children in particular, because children's aspirins are what? Grape flavored or cherry flavored or orange flavored, you know, because aspirin probably by itself is probably pretty nasty, you know, unpleasant taste. So what happens is anything that makes remember what happens to stuff we eat, everything we eat and drink ends up in our blood. If someone takes a lot of aspirin, it's going to drive their blood more acidic because you're taking acetylsalicylic acid. So that's going to drive us into metabolic acidosis. Here's one, a person who why would they do this? A person that overuses laxatives, you know, why would they, you know, how do you overuse laxatives? I'll just throw that out there. I'm sure they do. I'm sure people do. But why? So when you have chronic diarrhea, which you would probably end up with overuse of laxatives, or you have some condition that causes chronic diarrhea, you're going to lose all your bases. So that's going to drive you into metabolic acidosis. Now remember, with metabolic, your CO2 is fine. It has nothing to do with your breathing rate. Metabolic alkalosis doesn't happen very often. This is the unusual one. Someone who takes lots of antacids. Someone who takes lots of antacids. I've told you about the person I used to know that would take the Tums, right? You know, go through you know, what is that but nothing but calcium carbonate? It's essentially, instead of sodium bicarbonate, it's calcium carbonate. It's a neutralizer. I'm sure that if she continued on that pathway, she'd be ending up in metabolic alkalosis. So also chronic vomiting, someone who, you know, vomits all the time, blowing off, you know, getting rid of their stomach acids. Now, metabolic acidosis, metabolic alkalosis is pretty rare, but it still happens. What you're going to encounter much more frequently is metabolic acidosis. So what happens? How do you tell them apart? Well, first of all, respiratory acidosis is the #1 acid-base problem. Respiratory acidosis is #1 acid-base problem. Yeah. Patients with emphysema, patients with bronchitis, patients with cystic fibrosis, narcotic overdoses that depress the medulla, that causes your anything that causes your breathing rate to drop or creates additional barriers for gas exchange, pneumonia or mucus, bronchitis, narrowing of the airways, cystic fibrosis, accumulation of mucus throughout the bronchi in here, lung function damaged, anything that's going to cause us to retain CO2. Your patient's going to be hypoventilating. So your breathing rate is slowed, or your gas exchange is poor. This is the #1 cause of this is the #1 acid-base imbalance problem right here. You depress the central nervous system, you slow down your breathing rate. Slow down the breathing rate, you retain CO2. When you slow down the breathing rate, retain CO2, you drive your pH down because you're forming more carbonic acid. So now, the range for CO2, the normal level of CO2 is between 35 and 45 millimeters of 35 to 45 millimeters of mercury pressure in the plasma. 35, the range is 35 to 45. Anything above 45 is going to cause a drop in your pH. The higher the CO2 levels, the lower your pH is. pH is above, a pH is going to drop below 7.35 if you're out of the range. There's a normal range of 35 to 45. Anything above 45 is going to start dropping your pH, because above 45 means you got more CO2. If you got more CO2, you're going to have more carbonic acid and become more and more acidic. So you do your blood work in your patient, and your pH is low and your CO2 is high. It's a respiratory issue. It's a respiratory issue. It is respiratory acidosis. If the pH is low and your CO2 is high, it's a respiratory problem. 35 to 45 is your normal range. Respiratory alkalosis, your pH is above 7.45. And your CO2 is below 35. Remember, the range for CO2 is 35 to 45. If it's above 45, your pH is going to be down. If it's below 35, your pH is going to be up. Remember, up is alkaline, down is acidic. So if you are in alkalosis, your pH is above 7.45 and your CO2 is down. Respiratory alkalosis, hyperventilation, your panic attacks, you're breathing rapidly. I don't want to do that too fast. So breathing rapidly. Yeah, I know. So I'm afraid to ask for a paper bag. You give me a plastic bag. So what happens here is you're blowing off your CO2. Your CO2 levels drop and your pH goes up. So your patient's breathing rapidly. All sorts of things drive your respiratory alkalosis. You're blowing off your CO2. So and this is why your ketoacidosis patient is so difficult to figure out. Because what does a ketoacidosis patient do? They're breathing rapidly. They are breathing so fast because the medulla thinks they've got too much CO2. So they're puffing but they smell like a fruit. And it's not going to affect her because it smells like juicy fruit gum, or fingernail polish. So they're breathing so fast and they smell fruity, but it's not going to help because that's not the cause of the low pH. Their pH is low because they got all these fatty acids in their system. As fast as they're breathing, they should be going into respiratory alkalosis. The giveaway with your ketoacidosis patient is they smell funny. Otherwise, you might assume that they're just having a panic attack and they're hyperventilating. Well, it looks that way, but the giveaway is going to be the odor, on this. Anyway, respiratory alkalosis and respiratory acidosis. Respiratory acidosis is the #1 acid-base problem. On the other side is if there's any other acid-base issue, it's metabolic. If it's not CO2, if the CO2 levels are normal, if the CO2 is between 35 and 45, then it is not respiratory. It's metabolic. So here we're looking at what's the pH. Take your pH, your blood work comes back in your patient, and they are above 7.45, but the CO2 is normal. Or it's below 7.35 and the CO2 is normal. That tells you it's a metabolic issue. If it's above, if it's below 7.35, it's metabolic acidosis if the CO2 is normal. If it's above 7.45 and the CO2 is normal, it's metabolic alkalosis. So, right away with a little bit of blood work, you know the pH and you know the CO2 levels. Right away now you can tell, is it respiratory? Is it metabolic? And that tells you how you're going to treat it. So, metabolic acidosis, the number 2 most common acid-base issue. Ketoacidosis is metabolic acidosis. Lactic acid is metabolic acidosis. Alcohol intoxication, excessive consumption of alcohol, is going to cause metabolic acidosis. Your patient will be breathing rapidly. They will be disoriented. The medulla is trying to compensate by blowing off the CO2, but it's not a CO2 issue. Your CO2 values are going to be normal. They're going to be between 35 and 45. It's not a CO2 problem. It is a metabolic issue. You can breathe as fast as you want all day long with ketoacidosis. It's not going to solve the problem. The problem with ketoacidosis is your cells are starving and they're trying to generate more glucose. So if we are below 7.35 and CO2 is normal, it is metabolic acidosis. The bicarbonate level is somewhere below 22. Bicarbonate range is 22 to 26. We are below 22. And we know right away that it is metabolic. Of course, the CO2 level is going to give it away for us easier. So, because you got to check CO2. If CO2 is normal, it is not a respiratory issue. Aspirin overdose can cause metabolic acidosis. People that drink antifreeze, they do. Some people do. People that drink Windex, anything with alcohol in it. Sterno, you all know what Sterno is? Sterno is jellied alcohol. If you've ever been to a buffet line and they have those little cans underneath there with the little blue flame there, they're keeping the buffet trays hot. That's Sterno. It's jellied alcohol and it burns. And an alcoholic will take that, buy a can of Sterno for a lot less than alcohol. And will buy that and wrap it up in cloth and squeeze it and squeeze out the alcohol and drink it. So
sounds like extreme.
You're an alcoholic, and you don't have a lot of money. What do you do? So you drink Sterno. They call it, the term is called squeeze. So what they drink. The well, I hope that's.
Is there something here?
That's how our body. Let's see what's going on.
I want to know some of those.
I know. Oh, okay. Sorry. Oh, wondering. No, that's okay. We were.
The section 2 thing, it's coming to this. Like it's on.
Oh, okay. It's okay. You're fine. Wasn't it?
That's why you were being nosy. I'm like, what are you being nosy for? I want to know.
I'm being nosy because I'm waiting for the anatomage and they're just wandering aimlessly in the
just
hall.
making you like fancy over here.
So,
I know, I heard
heard keys earlier and I was like, oh.
Yeah, I know. I just want to get this class done before they bring the machine in. So anyway, a lot of alcoholics can drink just about anything that would kill a normal person. So a normally healthy individual. You know, we don't usually drink methanol. Methanol is wood alcohol, and that usually kills you after about a week, but you go blind halfway through the process and you don't recover.
That's why I like. Sorry.
Go ahead.
My high school chemistry teacher told us the story of how her brother and his friends, homemade moonshine, the one friend went blind because.
Right, because of wood alcohol in there.
Well, he went blind first and then he died.
Yes, and that's the sequence. It destroys the optic nerve, and it can't be treated. Back during Prohibition era, back in the 1920s, lots of people died from drinking homemade moonshine or homemade alcohol they distilled themselves, but we're using wood chips in the process, or we're using copper tubing that wasn't clean. So anyway, metabolic acidosis, the number 2 acid-base problem. It depends on a lot of things here. Anytime we generate acids in our body, metabolic acids like lactic acid, for example, or we ingest lots of acidic substances like aspirin, I guess somebody could try and want to kill themselves with that. I guess if you took enough, it might work. Anyway, the treatment for metabolic acidosis is just make them breathe faster, because there, it's increased ventilation until the kidneys can get this treated. Now, metabolic alkalosis, your pH is above 7.45. Remember, pH, normal pH is 7.4. 7.45 and above is alkaline, 7.35 and below is acidic. Anything that drives us one way or the other is going to drive us into acidosis or alkalosis. Now here, again, the key is carbon dioxide. Carbon dioxide is 35 to 45. CO2 comes back perfectly normal. Okay, so it's not CO2. The next thing is you look at your pH. Your pH value tells you, is it acidic or is it basic? Is it acidosis or alkalosis? So if it's, the magic number is 7.4. Above 7.4, you're alkalosis. Below 7.4, it's acidosis. CO2 is normal, then it's not respiratory, it's metabolic. So right away, all you need to know is the pH and the CO2 level. And that'll tell you. If CO2 is too high or too low, then it is it's going to be if CO2 levels are outside the range, it'll be a respiratory acidosis or a respiratory alkalosis. Metabolic alkalosis, chewing up lots of Tums, excessive vomiting, high levels of aldosterone can drive you into metabolic alkalosis, because aldosterone tells you to retain sodium and retain water. You can, I guess because you're diluting the CO2, I don't know exactly. I can't, off the top of my head, figure out the role of aldosterone here, but I'm sure there's something good. So anyway, metabolic alkalosis. So now one of the things we see is if it is a metabolic issue, first of all, metabolic alkalosis is pretty unusual. So here's the way you check. I've been saying this, but here it is in one screen. Check for pH. If it's below 7, it's acidic. If it's above 7, it's alkaline. Check the CO2. CO2 range is 35 to 45. If the pH is below 7 and the CO2 is above 45, it's acidosis, because Higher CO2 causes more carbonic acid. If it's below 35, it's alkalosis, less carbonic acid. So if pH is below 7, check the CO2. If pH is above 7, check the CO2. If the CO2s are normal, it is not a respiratory problem. So once you know the pH and you know the CO2 levels, you can say, is this a respiratory issue or a metabolic issue? If the CO2 is normal and you're acidic, it is metabolic acidosis. If the CO2 is normal and you're basic, it is metabolic alkalosis. But if the CO2 is low and your pH is high, it's respiratory alkalosis. All you need to know is the pH and the CO2 levels. Don't, bicarbonate's nice to know those numbers too, you'll get those. But the two key things you need to make that distinction are CO2 and pH. Because at least pH will tell you right away, are you alkaline or are you acidic? So you're either dealing with acidosis or alkalosis. That's the first thing you'll learn from pH. Then you check the CO2, and the CO2 will tell you it's either going to be a respiratory or a metabolic issue. If CO2 is normal, it is not respiratory. Now, how do we fix it? If it is a respiratory problem, the kidneys will compensate. If it's a respiratory problem, the kidneys will compensate. If we have trouble with gas exchange, if the breathing rate is depressed, if the breathing rate is elevated, the kidneys will compensate by either retaining or secreting hydrogen ions. However, if it's a metabolic issue, the lungs will fix it. You breathe rapidly in ketoacidosis. So the lungs are trying to fix the problem. Ketoacidosis, you are too acidic. Your blood work comes back and says, well, pH is 6.5, but the CO2 is normal. The lungs are trying to fix by breathing rapidly to blow off the CO2, which isn't really there. So whatever the problem is, the other system tries to fix it. If it's respiratory, the kidneys try to fix. If it is metabolic, the lungs try to fix. So always think of ketoacidosis as your example. Ketoacidosis is the #1 metabolic acidosis issue. Let me say it again. Ketoacidosis is the #1 metabolic acidosis issue. Do I need to say it again?
Mm-hmm.
Respiratory ketoacidosis is the #1 metabolic acidosis issue. Okay. Now, okay.
She used to buy product first.
She's only using one.
I know.
I just felt so much.
Ketoacidosis is the #1 metabolic acidosis issue.
Got it.
Okay. Now, all you need to remember, all you have to remember on any of this stuff, on acid-base balances, is check the pH. The pH will tell you immediately, are they in acidosis or alkalosis? Check the CO2. If the CO2 is normal, then it is metabolic. If the CO2 is out of range, it's respiratory. All you need are those two values, CO2 and pH. pH will immediately tell you which way it is on the scale, acidic or basic. Check the CO2, then the CO2 will tell you if the CO2 is normal, it's not a respiratory problem, it's metabolic. If the CO2 is abnormal, out of range, it's not metabolic, it's respiratory. It's really straightforward. And I think that there are some practice questions on the practice exam for this that give you some examples.
There
So,
was some on the RP.
yeah, so make sure that you take a look at those because I mean, it's easy to get confused on this. That's why I've been going over it and over and over it for you. So, okay, so I've got 15 minutes. I'm going to start respiratory. So now let me get back to where I was. Let me. Oh, I am sharing. So everybody can see the respiratory system on here, I hope. So, by the way, that was the end of Unit 4 too, on when we finished fluid and electrolytes.
So this is.
This is start of Unit 5 now. And I'm going to take the next 15 minutes to try and get us going on this. So, okay. In lab, we went through all the anatomy of the respiratory system. So we're not going to spend a lot of time on anatomy here. We're going to talk about the physiology behind breathing. Now, when we breathe, the respiratory system's primary role is to give us oxygen and get rid of CO2. And so we have 4 terms here. Pulmonary ventilation, moving, that's what we call breathing. Air into the lungs, out of the lungs, into the lungs, out of the lungs. External respiration, lungs giving up oxygen to the blood, blood giving up CO2 to the lungs. Transport is the movement of the 2 gases to and from the lungs and the tissues. We put oxygen into the blood. It's delivered to the tissues give up CO2 into the blood, and that's brought to the lungs for removal. And then the internal respiration is the exchange between the capillaries and the cells. Exchange between the capillaries and the cells themselves. Every cell is in contact with at least 1 capillary, maybe more. Alveoli have up to 100 capillaries wrapped around them. But that's sort of what they do. They give up oxygen and gain CO2. This is what our alveoli look like. The alveoli, we've got a question. Okay, 2 comments. I can't see the respiratory PowerPoint. Okay, I thought we were there. Let me go back and bring it up again. Okay. Try the hang on 1 second. Screen share. Can you see it now? The respiratory. Yes, no, please. Yes, great, thank you. Okay, so it was telling me I had it up, but I guess it was not being truthful. So, okay, let's get on to where I was now. Okay, the alveoli are the site of gas exchange in the lungs. This is where gas exchange takes place. The alveoli are 1 cell layer thick, made of simple squamous epithelial cells. They are covered with a layer of elastic fibers. They are very resilient. They expand and contract. They're surrounded by smooth muscle, and they're covered with capillaries. And they're all contained, they're contained in sacs. They have pores that connect to other alveoli to maintain air pressure. So the air pressure in one alveoli isn't higher or lower than the one adjacent to it. We keep the inside lining of the alveolar surface sterile with surfactant to keep us from sticking together. We have macrophages that kill everything in sight that might be a pathogen. So we're breathing sterile air. And the alveoli actually expand and contract as air goes into them and comes back out. One of the things about emphysema, the emphysema is a disease that destroys the elasticity of the alveoli itself, so that the alveoli will ultimately, in a patient with emphysema, the alveoli will expand as air comes in, but they can't relax to push it back out. And so a patient with emphysema gradually develops what we call a barrel chest, because they're trapping and retaining air. Their lungs develop these huge bubbles on them, and the lungs get bigger and bigger and bigger. And they tend to have, in many cases, your emphysema patient becomes a candidate. If they're healthy enough, they got to be sick enough to have it. They got to be healthy enough to survive the surgery. It's called lung reduction surgery, and they cut out the inflated areas of the lungs. So it's like you're healthy enough for the surgery, but you got to be sick enough to have it. So, okay. The membrane is one cell layer thick. It is about 0.05 millimeters, I think, of in size. Gases go across these layers very easily. Oxygen has a limit to how far it can go through diffusion, but the thickness of the cell layer of the alveoli and the thickness of the capillary wall stay well within those ranges. So gases can diffuse across passively very, very easily. This is what the alveoli look like on the inside, made up of these simple squamous epithelial cells. Remember, it's open to the outside, so they're definitely epithelial. Most of the cells are going to be what we call type 1 cells. Those are the simple squamous. The other cells are going to be type 2 alveolar cells. They release what's known as surfactant. Surfactant is a substance that keeps the cells from sticking together. It keeps, we're dealing with one cell layer thick. We don't want them to fold in on themselves and adhere to each other. So the surfactant is like a detergent. It breaks the surface tension so that the alveoli stay inflated. Now, the whole idea behind breathing depends on changes in air pressure inside the lungs. Now, our bodies are under a great deal of pressure from the air. The pressure of we're at the bottom of a gigantic column of air extending way up into the stratosphere. The pressure of that air pushing down on us is about 760 millimeters of mercury. We don't notice it because, we are exposed to it all the time, so we don't feel the pressure. However, it is pushing down on us all the time. That air, the pressure of the atmosphere, pushing on us constantly, 760 millimeters of mercury pressure. Now, how do we get air into the lungs? We have to lower the pressure of the air inside the lungs so that it is less than atmospheric air pressure, so that air gets sucked in. How do we breathe out? We raise the pressure inside our lungs higher than the outside air. So we simply move, our air simply comes in as the pressure inside our lungs drops, because outside air pressure is higher than the inside, so it just pushes its way in, and our lungs, we suck in air, and we blow it out because the pressure now in our lungs is higher than the outside. So suck in, blow it out. We are on our own scale, we are raising the pressure and lowering the pressure relative to what's going on around us. Air pressure around us isn't going to change. It's still about 760 millimeters of mercury. We have to try, and the only way we can breathe is to, work around that pressure. So we have pressure in the alveoli. We call it the intrapulmonary pressure. We have pressure within the pleural cavity. Remember, the pleural cavity is the cavity that's between the visceral pleura and the parietal pleura. The lung has two layers of serous membrane on it. Visceral pleura sticks to the surface of the lung. Parietal pleura sticks to the inside surface of the chest wall, and the area in between is filled with goopy serous fluid. And it's there so we don't have any friction. That is the pleural cavity, or the, we say the intrapleural pressure, the pressure on the outside of the lungs pushing in. So we have pressure inside the lungs pushing out and pressure outside the lungs pushing in. The pressure inside our lungs, the air pressure inside our lungs will always equalize with the air pressure around us as we breathe. Every time we take a breath, even though we drop the pressure in our lungs to suck air in, eventually that air has to come back out, and now we are equal with the outside air pressure. So we're always going to equalize back and forth, back and forth, back and forth. The pressure in the pleural cavity is always going to be less than the air pressure and the pressure in the lungs. Now think about this for a second. If the pressure inside the pleural space was hot, if it was higher than what's inside our lungs, could our lungs ever expand? Because if you're pushing in with a real, if you've got the pleural space there with the visceral pleura on the lungs and the parietal pleura on the, excuse me, on the chest wall, and the pressure in there is pushing in constantly on the lungs, and you can't overcome that. You ever gonna go take a breath? Yeah. So that pressure has to be less than what's inside the lungs. It has to always be less than the air pressure. It has to be less than what's inside the lungs, or we'd never be able to breathe.
Is that why it's harder to breathe when we're like at higher elevation?
Exactly, because there is less air. There's less air pressure at higher elevations. Every 10,000 feet you go up, the air pressure is cut in half.
I feel like I breathe easier in higher elevation.
Well, you get used to it.
My
It's
South Georgia air compared to East Tennessee air feels like it's a lot easier and lighter to breathe up here than it is down there.
Might be elevation. It might be moisture content. Moisture, content affects a lot of the ability to breathe. We say the air is heavy today because it has it's retaining a lot of moisture. That might make it more difficult.
It's a lot different than Ohio too. Where I used to live, it was close to the lake,
Mhm.
so there's a lot of humidity all the time.
Yeah.
So it's I don't remember if it's like easier or harder, but like it's a lot different.
Well, the more water, that air that's warm retains a lot of moisture, and sometimes it just feels, and that moisture, it's gonna coat the inside lining of our lungs more than we want it to, making it more difficult for gas exchange to take place. So we don't.
So it's not so much the elevation as it is the humidity difference that
Probably,
makes it easier.
probably. Now, if we,
Easier to breathe.
yes, now if we go up 10,000 feet, we'll have difficulty breathing because the pressure's lower, but we'll accommodate for that by making more red cells in a couple of days. The air at 10,000 feet is likely very cleaner and drier than what we're used to. So, and that may also be, the problem with it, if it's drier, is it may dry out the inside of our lungs a little bit more too. So there's always going to be some sort of trade-off with breathing. We don't want to, we always have to keep the pressure though in the lungs and the outside air greater than what's between the layers here. Now we go to 10,000 feet and our air pressure cuts in half, it's harder to breathe. Partly because the oxygen level is cut in half, but also because the pressure is lower. So our pulmonary, the pressure between the layers finally gets a chance. Hey, look at me! I'm almost as strong as the outside air. So, but the whole ability to breathe depends on pressure from the outside against the inside. So, and our lungs don't help us. And this will be our last point here. Our lungs aren't going to help us because the lungs are elastic and they're always going to shrink. They're always going to shrink down to their smallest possible size. Like a balloon will always shrink down. You know, when you let the air out, it will always come down to its smallest shape. And the alveoli will always shrink. They're also elastic. So the lungs are always going to want to shrink down, and you have to force them back out to a larger size. But the chest wall is working against that, because our chest wall is going to be expanding every time our intercostal muscles contract. Our chest wall goes out though, and the lungs go with it. That forces the lungs to reopen. So we're constantly at a battle going on here. So, okay, that's a good place to stop for right now. You know, after all that respiratory and metabolic acidosis and alkalosis, I don't need to confuse you with pressure relationships. We can save that till Monday. So, okay, any questions on anything?
So what we just finished.
That's,
But we don't have, I thought exam 5 was the final.
no, there's exam 6 is the final. There's 6 exams. The final exam is the last test. Yeah, there are 5 unit.
So we have lecture test 4 and 5.
Lecture test 4 is,
Then an exam.
and lecture test 4, lecture test 5, and then the final. Because I still have to
I
talk about.
thought I was stressed already. Now I'm really stressed.
Okay, don't tell her about the final exam. We'll pop it on her next week. Okay?
Yeah, just give me a week to take it.
So.
We're done with lab, right?
Oh yeah, we're done with that.
That's what I literally thought yesterday was Thursday. Like,
So,
it's not.
okay. So does anybody have any questions other than the fact that the final is coming up in 2 weeks?
Okay.
Okay. Then I will
Oh my gosh.
get us out of here, and I'll see you all on
It's
Monday.